Hello, this is Mrs. Angela T, and this video is for H1 Chemistry on the topic Chemical Energetics. This video is to show you how to correctly substitute values of M, C, and delta T when doing calculations using data from calorimetry. So take a look at this worked example here. Let's gather some of the data given. In this worked example, notice that you're using 100 cm cube of 0.5 moles of silver nitrate aqueous that's placed in a plastic bottle, and then you're adding potassium chloride aqueous to the mixture. So let me just draw this out for you in a diagram. Very simply, you have a plastic bottle or a beaker. So initially you've put in 100 cm cube of your silver nitrate, and then you've added in another 100 cm cube of potassium chloride, so another 100. So now these two total together will be 200 cm cube. The solutions were initially at the same temperature, and after mixing, the temperature of the mixture was found to have risen by 7.5 degrees Celsius. So you put in a thermometer in this whole solution here, thermometer here, and it's measured a rise in temperature by 7.5 degrees Celsius. Now this is very important because a rise in temperature tells you that the reaction is exothermic, and therefore your enthalpy change is expected to be negative. Please write all these down in your notes. Then the question is over here, calculate the enthalpy change of the reaction. So here's the quick guide. The enthalpy change of the reaction, you need to use this formula because it's an exothermic reaction. There's a negative sign put here purposely because it's exothermic. You need to substitute in values of M, C, delta T, and divide that by the number of moles of limiting reagent. As easy as that looks, because you can easily memorize the formula, many students fail because they forget the negative sign. Many students fail because they do not know what the M value is. The easiest to always substitute is the delta T. Okay, but what is M? Sometimes even the C is wrong. So this video is to show you how to get the M especially correct. The easiest is delta T because delta T is a change in temperature. It is 7.5, so let me just fill that in. Now whether it is 7.5 degrees Celsius or 7.5 Kelvin, it doesn't matter. And the reason why I change it to Kelvin is because the specific heat capacity is given in per Kelvin. So I'm hoping in the end, after substituting everything in, the Kelvins will cancel out. A temperature change of 7.5 degrees Celsius is the same as a temperature change of 7.5 Kelvins. C is a constant and is given as the specific heat capacity of the solution. It's also the specific heat capacity of water because these are aqueous solutions, so the majority of molecules in there are water. So the specific capacity is given as 4.20 joules per gram per Kelvin. So the Kelvin here and the Kelvin here will cancel out. So we've got delta T done, C done. Next is the M. M can be mass or volume, so refer to the top of the page to write down the value of M. Now if you look at this diagram here, notice that the delta T that you're measuring, the change in temperature, you're measuring the change in temperature of this entire solution, that is 200 cm cube. Then the heat capacity of solution refers to the whole solution as well. Remember, M times C times delta T all must refer to the same thing. So if delta T refers to the temperature change of the entire solution and C refers to the specific heat capacity of the entire solution, M must refer to the mass or volume of the entire solution. So it's not just 100 because you're mixing two together, it's actually 200. So M is actually 200 cm cube as obtained from the information given in the question here. But it's also okay to convert it to 200 grams because the density of water is 1 gram per cm cube. So 200 grams is 200 cm cube. And why did I convert it to grams? So that later when I substitute in the grams in a specific capacity and the grams of the mass will cancel out. So therefore the heat change MC delta T, let me just add it all, multiply it all together. M is 200, C is 4.20, delta T is easy 7.5. Notice I didn't put the units in the working because all the units will eventually cancel out, leaving me with 6300 joules because this joules here doesn't cancel out. I convert that to kilojoules, 6.30 kilojoules. Okay, so this is just heat change. There is no sign here for heat change, only sign for enthalpy change. Okay, next part you need to work out enthalpy change. So you need to find the number of moles of limiting reagent. The number of moles of silver nitrate used and the number of moles of potassium chloride used are the same. So in this case, because the mole ratio is 1:1, there is no limiting reagent. So in this case, pardon me. So in this case, the number of moles of each, they are the same, and that would be the concentration times volume. That means you just find the number of moles of one of them because it's the same. Okay, so this would give you a value of 0.0500 moles. So that's the number of moles of the reagent, because neither are limiting. So the enthalpy change would be mc delta T, which is 6.30 kilojoules. Notice from joules I convert to kilojoules. Divided by the number of moles, which is 0.0500, and don't forget to add in the negative sign because it's a temperature rise. So you have to put this in yourself, it's not going to appear magically. And then the final answer you get is minus 126 kilojoules per mole. If you didn't convert this to kilojoules earlier, then your answer will be in joules per mole, so it's 126000. So this is the example given here. The next example is the exact same reaction, but this time, similar to the worked example earlier, instead of using 100 cm cube of 0.5 mole per dm cube of silver nitrate, I decided to use 150 instead. Now because now the total volume has increased, the temperature change will be less than 7.5. Okay? So in this case, I just want to identify what would be the M, the C, the delta T, and the number of moles of limiting reagent. I do not want to go into finding the enthalpy change because it would be the same as the previous question. So in this case, notice we start with 150, so we have a container here. We start with 150 cm cube of silver nitrate, and then we added in 100, so altogether will be 250 cm cube. And then we do the same thing, so write down the values of mc delta T. So delta T is mistake. Delta T is actually 6 degrees Celsius, which also is 6 Kelvin. The C is the constant, and your M in this case would be 250, not 200 like in previously. So the heat change in this case would be 250, that's your M. Then your C is 4.20, delta T would be 6, and the answer would be 6300, which is the same joules, also 6.30 kilojoules if you wish to convert. Now, we need to find the number of moles of limiting reagents. So you actually, in the exam, if this comes out, you need to find the number of moles of each of the reagents and then find out which one is limiting. So the number of moles of silver nitrate would be 0.5 times 150 over 1000 equals 0.0750 moles. That's the number of moles of silver nitrate. Then the number of moles of potassium chloride will be concentration times volume, which is 100 over 1000 would be 0.0500. You need to show these two working and then conclude that, hey, this is the number of moles of limiting reagent. This is the limiting reagent. And then you can go on to find enthalpy change. Okay? So let's take a look at the next example. The next example is different. Because these two examples, you're mixing two solutions. The next example, we're mixing solid and into a solution. I purposely chose this example because some students who are very blur, the MC delta T, they see, hey, M is 10 grams. And if you understood the procedure earlier, you would know that 10 grams is totally wrong. So let's take a look at this one. Heat change MC delta T. You're essentially adding 10 grams of metal into 250 cm cube of solution. So your 10 grams of metal goes in. Okay? And then here is 250 cm cube. What we do is, in order to avoid complication, you don't total up the two masses. We usually assume that the solid mass is negligible. So the M that we use is actually only 250. So please take note of this convention here. So when you stick your thermometer in and measure the temperature change, we assume it's just 250 because this 10 is negligible compared to 250. So that is your M. The C, notice, is a constant, 4.20. And then your delta T, that's always the easiest, is 14.2 degrees Celsius or 14.2 kelvins. And notice that the question says the solution has increased in its temperature, so we would expect this to be an exothermic reaction as well. Okay. So the number of moles of copper sulfate used, because the question already told you that the metal is in excess, so all you need to do now is to find the number of moles of limiting reagent. So the number of moles of limiting reagent would be the concentration of copper sulfate multiplied by the volume of copper sulfate. That would give me 0.0500 moles. Now over here I forgot to fill in is 14910 joules. If you want to convert it to kilojoules, it's 14.91 kilojoules. Okay, so I've got my MC delta T, I've got my number of moles of limiting reagent. I would assume that the enthalpy change of reaction is just MC delta T over number of moles of limiting. But go back to an earlier, the earlier part of your notes. Notice that when we look at enthalpy change, we're always looking at the number of moles. So in this case, the number of moles of copper sulfate is over here. In the equation, there are 3 moles of copper sulfate. So when you divide the heat change over the number of moles of copper sulfate, you're finding the heat change per 1 mole of copper sulfate. So to find the enthalpy change of this given reaction, you need to times 3 because of the coefficient over here. So the enthalpy change would therefore be 3 times, then your MC delta T is 14.91 over 0.0500, which is your limiting reagent. And because it is an exothermic reaction, you need to make sure there's a negative sign here. And the final answer is minus 895 kilojoules per mole.